Okay, now to prove the equivalence between Clausius and Lord Kelvin's statement, let's just first discuss how a heat engine thermodynamic cycle works. So we can represent it like that. This is called actually the tricycle formalism. So okay, you can represent the engine like this. And let's suppose that in this edge of the triangle it represents the contact of your system with a heat source at a low temperature, T cold, and this edge here represents the part of time in which your system is in contact with hot heat source at temperature T hot. So that's your system in there. And okay, so what happens is that in the cyclic operation, in the cyclic protocol that you're running on your system, there will be some heat which is coming from the hot bath into your system. So this heat, we're going to call it Q hot, and it's going to be positive according to our sign convention. And then part of that heat, sorry, that's not what I wanted to do. I wanted to make something like that. So part of this heat is going to be released into the coldest bath. Okay, so this heat is going to be negative according to our sign convention. We are going to we can just call it Q being negative QC, but to make it explicit that it's negative, we can write it as minus its absolute value. And the imbalance or the difference between these two things is, again, this is not what I wanted to do. The difference between these two things is going to be delivered as work, and this work is going to be made on the environment. Okay, so wait, now I'm pressing the wrong buttons all the time. So this would be some work. So again, remember the first law of thermodynamics. It says that the change in internal energy equals the heat plus the work. So because we are doing a cyclic process, there is no change in the internal energy in a round trip. So this is going to be 0, and 0 equals the total heat, which is the hot heat and the cold heat, and then the work, which is just the work. But again, we have said that the signs of these things are definite. So the cold heat is going to be negative, and I can write it like that. And this means that the work, actually the work also is going to be negative. I didn't say that before, but it's work performed in the environment and not onto the system. So this quantity here is also a negative quantity. So we can write it explicitly like that. This is minus the absolute value of the work. So in the end, from here, we can write that the absolute value of the work, which is the work made on the environment, is equal to the imbalance between the heat which has been consumed from the hot source and the heat that has been dumped into the sink, into the low temperature bath. Okay, and if I want to write it properly with the sign, I would say that this is minus the imbalance between QH and QC, which is negative in an engine. Okay, so if it is negative, we are talking about an engine. Fine. So now that we know what an engine is and how the engine works, we can prove the equivalence between Clausius and Lord Kelvin's statement, and we're going to do it as follows. So we're going to see that not Kelvin, so if Lord Kelvin's statement is not true, and this implies not Clausius. And then Clausius. And then we're going to forget about this and say, okay, let's suppose that Clausius' statement is not valid. Then we will see this implies that Lord Kelvin is not valid either. Okay, and saying that there is an if and only if between the negation of something and something else is the same thing as saying that Kelvin statements implies Clausius' statement, and vice versa. Okay, so let's see that. and for this, let's first say that Lord Kelvin's statement is not true. So in that case, I would be able to take a heat bath, okay, it's at some temperature, let's call it T cold, and we will be able to take a system, S, and this system, cyclically operating, is going to be able to extract some amount of heat from this heat bath and to deliver it as work. Okay. So then we saw this actually in the previous chapter when we were studying the mechanical equivalent of heat. We know that it's very easy to turn mechanical work into heat by means of friction. Okay, so we could have some dissipative process, some dissipative forces here that take all of that work and transform it into heat. And then we are free to put that heat wherever we want to put it. Okay, so this heat in particular could go into a reservoir at some temperature TH. Okay, and if TH is larger than TC, then we are violating Clausius' statement of the second law, because all what we're doing here is to take heat from a source at a definite temperature into another heat source at a larger temperature, and this is not allowed. Okay, so we have just seen that if it is possible to violate Kelvin's statement, then Clausius' statement of the second law is automatically violated as well. Okay, so let's now try to see the other side of the problem, which is if Clausius' statement is violated, then Lord Kelvin's statement must be also violated, or can be also violated. Now for this, again, similarly, let's assume you have a heat source at temperature Tc, and like we say, let's assume Clausius' statement is not true, so it means I can devise a process running on a system in which I can extract some amount of heat, Q cold. This is positive because it's entering my system, and I can take that heat here into another heat source. In this case, the heat is going to be negative, so we can make it explicit, writing minus its absolute value. It goes into a reservoir at temperature T hot, which is larger than T cold. Okay, so this is violation of Clausius' statement of the second law. So now that we know what a heat engine is, we could put a heat engine here. Okay, so some engine, and this engine is going to run between this heat source and that heat source. Now, one thing that I did not say is actually very important is when I talked about this Planck-Kelvin engine statement of the second law, it says here that it is impossible to devise a cyclically operating device that can absorb energy in the form of heat from a single thermal reservoir and deliver it as work, which it means is that it is impossible to make an engine functioning only with one heat source. You need at least two. It doesn't mean that you cannot have an engine with more than two heat sources. You can, and we will see examples of that. For instance, the ideal the ideal Otto cycle is a clear example of an engine cycle that works and performs work, but it performs work using more than two heat sources. But at least you need two because of the second law. Okay, so that was an important remark that I did not make in the previous video. And coming back to our proof of equivalence, now I'm saying that I can run an engine cycle between two heat sources. That is allowed by the second law of thermodynamics, okay? And this cycle will, like we saw before, take some heat from a high temperature bath, QH, this is going to be positive, and then we'll release some heat, okay? This heat, we can tune it in such a way that it's in absolute value, it is exactly equal to the heat that was absorbed by this other system S. Okay, so this heat released is going to be negative and exactly equal to minus absolute value of QC. Okay, and then some work is performed, which is equal to the imbalance between these two things. So it's actually the Q hot minus the absolute value of QC. Okay, so yeah, that's the work performed. So in this whole process, if you look at it globally like that, okay, so what is happening? Well, here I am taking some heat from the cold source, but in the end I'm putting the same amount of heat back into the cold source. So overall, when I run a cycle off my system and off my engine, and I stop and look what has happened, I have not absorbed any net heat from the cold bath. But in contrast, I have absorbed heat QH minus QC from the hot source. Okay, and I am producing some work out of this process. So what I'm doing is I'm taking heat from a given heat source at some definite temperature and transforming all of that heat into work. Okay, so it's the amount of work that I'm performing is exactly equal to this imbalance, because that's what we saw before that an engine does. Okay, so by this simple reasoning, we have proven that although they look pretty different, stating Clausius' statement of the second law or Lord Kelvin statement is the same thing. Depending on what we want to do with it, one statement can be more useful than the other, and we are going to see that later in this chapter.